Hello, everyone. Welcome to the April 22nd edition of Math 262. Reminder that you have a web assignment due on Friday. Today, we're going to finish up section 10.4, where we look at some more graphing of polar coordinates, and we're going to look at some calculus involved with it. So there are a couple types of curves that you want to be really familiar with. So let's look at this polar graph. This polar graph is super easy. It's just the radius is always 2. And so you can probably guess that this is just the graph of a circle with radius 2. Another type of equation that's pretty simple is theta equals pi over 3. That's where we let the radius be anything we want. And then we have the line theta equals pi over 3. You might be asking, what line is this? Well, it's a line through the origin, and we know the slope. So we know that the tangent of theta is equal to y over x. So the tangent of theta here is the tangent of pi over 3. So that's this triangle where this is 1 root 3, 2. So this is root 3, and that's y over x. So this should just be the line, y equals root 3 times x. And one more graph that might be a little more interesting is the graph r equals the secant theta. Now that's 1 over the cosine of theta. So you might be wondering, I'm not really sure what graph this is. Well, let's take a look. We know that this is the same as telling us that r cosine theta equals 1, which is the same that x equals 1. And so this is actually the vertical line at x equals 1. And that's the graph of that one. So you've seen a series of polar graphs that look a little bit different, or very different in polar coordinates than they did in rectangular. So I want to actually look at a couple curves and Desmos that we saw last time. And here we go, Desmos. So this is the curve r equals 2 sine of 3 theta. This is actually called a 3-leaf rose. You might have seen it if you did this in high school. It's a very pretty curve, it has 3 petals. The other one is the curve right here. It's actually called a limacon. This one is a cardioid because it's got that little cusp at 0. There are also limacons with a loop and ones without a loop. So these are types of polar graphs. And there's actually something in the book, I'll show you right here, that goes into depth what all these different shapes should look like. So I'm not going to go into too much depth about what they all are, but just know that when you see these different forms of the equation here, you see them on the left-hand side of the chart. There's different forms that these take. And so when you see these types of equations, you know you're getting some kind of graph that looks like one of these. Okay, so let's go back to our whiteboard. And now it's time to do slopes and tangent lines with polar coordinates. Okay, so let's take a look we have the function r equals f of theta. Well, what do we know? If r is f of theta, this is telling us that x is equal to r times the cosine of theta, which is the same as f of theta times the cosine of theta. And y is r times the sine of theta, which is f of theta times sine of theta. What do we notice about these two equations we've written down? Well, I think what you'll notice is that they look just like the kinds of parametric equations we saw in the, in section 10.3. So what this should tell us is if I want to find my tangent line, it's dy d theta over dx d theta, where I have these equations for y and x. And so I see that I need to use the product rule to calculate what these derivatives are. I get this lovely expression for the slope of my polar graph at theta. So obviously we want to avoid places where dx d theta is 0. But we actually can make the following observations about what's going to happen. So whenever dy d theta is 0 and dx d theta is not 0, we're definitely going to get a horizontal tangent line. When dy d theta is not 0 and dx d theta is 0, I want you to pause the video and think about what happens to our tangent line. Well, you can probably observe that you get a vertical tangent line. And when they're both 0, we just don't know what's going to happen. There are lots of things that could happen. It could be a vertical tangent line, horizontal tangent line, or neither. So you just don't know when they're both 0, and that's not surprising because it should remind you of L'Hopital's rule. So let's do an example where we look at the equation r equals 2 cosine of theta. So first I'm going to find the equation of the tangent line at theta equals pi over 2. Well, I need to find what dy dx is. So that's equal to dy d theta over dx d theta. Okay, so that's going to be minus 2 times the sine of theta times, I believe it's sine of theta, plus 2 times cosine theta times cosine theta over negative 2 times sine of theta times cosine theta minus 2 times cosine theta sine theta. Okay, so if I simplify this a lot, what I should be getting is minus 2 sine squared of theta plus 2 cosine squared of theta over, I believe it's negative 4 sine theta cosine theta. I'm going to plug in pi over 2. Well, what do I see happening in the numerator is I'm getting 2. And the denominator, I'm getting 0. So this should say I have a vertical tangent line. All right. So well, what's the coordinate? So the coordinates, when theta is pi over 2, my coordinates are cosine theta or sine theta, which should equal, let's see, 2 times cosine 0, comma, 0. So that means that my tangent line is just x equals 0 because it's vertical. Okay, so now let's find all points with a vertical tangent line. Okay, well, we want the denominator to be 0, so that tells us that 4 sine theta cosine theta equals 0, and that happens at theta equals 0, pi over 2, pi, and 3 pi over 2. But they might not all work. So we need to know, what about dy d theta? That is -2 sine squared of theta plus 2 cosine squared of theta. Well, that's actually equal to 2 times the cosine of 2 theta. So when is this 0? This will be 0 at when theta equals pi over 4. I think 3 pi over 4. Five pi over 4, 7 pi over 4. And it turns out that these actually give you the same points as the other. So we know when we should be getting, those were vertical, and these are actually going to lead to the horizontal tangent lines. And so now let's actually find the points. So when theta equals 0, that gives us the polar coordinate. So the polar coordinates are r theta, where r is 2 cosine theta. And so when we have theta 0, this is giving us the coordinate 2, 0. When theta is pi over 2, this is giving us the coordinate 0, comma pi over 2. Those were the vertical tangent lines. And when theta is pi over 4, this is giving us the coordinate root 2, comma pi over 4. And when theta is 3 pi over 4, it's giving us the coordinate negative root 2, 3 pi over 4. And so these are the points with the vertical tangent line, and these are the points with the horizontal tangent line. Now, if I want to find the rectangular coordinates, that's not so bad. The rectangular coordinates are actually 2, 0, 0, 0 for the vertical tangent lines, and they are, I think, 1, 1 here. This one's a little trickier. Let's see, I think it's going to be 1, comma, -1. So let's look at a graph of this on Desmos to see that that's right. Well, here's our equation, and we see the points at 0, 0 and 2, 0. We're definitely getting vertical tangent lines. And at the points 1, 1 and 1, -1, we are getting horizontal tangent lines because this is the graph of a circle. So the exercise I want you to do is find the points where the tangent line is vertical, horizontal for the polar equation 1 minus sine of theta, and use Desmos to check your answer. Let me know if you have questions.